Where there is a will, there is always a way. So hello my shimmering stars, I Shaurya is going to start one short video lecture on states of matter. Students, in our victory batch, we have already covered lectures on physical chemistry, and this is going to be very interesting chapter. So first of all, the question arises in our mind that what is states of matter? So in our class 10th standard students, we have already covered about classification of matter. And when we were classifying matter, we classified in two subcategories, that was solid, liquid and gas. Why it was classified, on the basis of what it was classified as solid, liquid and gas, the question arises. Students, there were two forces due to which it was classified. Now these two forces are what? One is force of attraction, another one is escaping tendency. Now let us write this. To determine states of matter, two forces act within the molecules or upon the molecules, you can say, which are, number first is force of attraction, number second students is escaping tendency. Escaping tendency. Okay. If I talk about both of these forces, students, we can understand it in a general way. For example, if I have a good bonding with my best friend, like I study with her during my examinations, I share my each and everything stuff with her. So that means I have a good bonding with her, right? So there is a strong force of attraction between both of us. But if I talk about someone who is not my well-wisher, I would say I would not recommend myself to, go and talk with him or her, right? So there will be a strong force of repulsion in between them. Now what happens in the case of molecule? The same thing arises there. If two molecules have a good force of attraction, then they will be held together. But if they don't have a strong force of attraction, there arises strong force of repulsion, due to which the molecules stay apart from each other. Like I said in the real life example, if someone is not my well-wisher, I would stay apart from that person. Why? So I will maintain a distance between the person. That means whenever there is a repulsion force, there is more of an intermolecular distance. But when there is, good bonding, good interaction, then the intermolecular distance is very, very less. That means they are held together. Now I will tell you these in the case of solid, liquid and gas. So we are going to write solid, then we are going to write liquid, and then we are going to write gas. See, for three of these cases, let us see for the case of solid first of all. The particles are closely packed like this. These are tightly held with each other in such a way that they don't have even space to move from one place to another. They just vibrate along its own position, right? If I talk about the liquid state, students, in liquid state we observe particles are present at a distance from each other. Likewise. But yes, there is a strong force of attraction in the case of liquid also, because liquid exhibit both of these forces, escaping tendency also and attraction tendency also. Okay, and if I talk about the gaseous one, students, what do we observe? The particles are present at a far most distance from each other. Right? Now here in the case of gases, what do we observe? We observe that here tendency of escaping is more as compared to the force of attraction. Clear? Now to differentiate all of these, one more thing I would say that, for example, this is my first molecule, this is my second molecule. Kindly tell me the intermolecular distance between each of these. As I told you, if I have a good bonding with someone, then yes, intermolecular distance is a quite less. I will call her and I say, let us come together, let us have a lunch together. So that means we are coming and having the activities together. That means intermolecular distance is less. Now if I have I do not have a good interaction with someone, I won't meet that person. That means the intermolecular distance is more. Same happens in this case. These are held together. Why? Because they have a strong force of attraction. These are apart from each other. Why? Because they have very less force of attraction. They have the tendency to escape from each other, to move apart from each other. So what would I say here? Intermolecular distance Here intermolecular distance, that is the distance between the two molecules, is less, very very less, because they are so closed. Here there is a distance more than solid, more than solid, and in the case of liquid they are at a far most distance. Other than this, I have already told you about both of these forces. They have strong force of attraction while repulsion is almost negligible. In this case, they have both of these forces acting upon. In liquid, the strong forces of attraction are not as much as solid, but yes, it has more than that of gaseous. And in this case, only if I talk about the tendency to escape from each other, it is less than gaseous. But yes, more than solids, right? So if I talk about the gaseous one, in the gaseous one, what do we say? Strong forces of attraction, not at all there. It's almost negligible. They have the tendency to escape each other more. Clear? Now students, moving further, if I talk about the gaseous one, because in this chapter we are going to talk about the gas only. So if I talk about the gas exhibit two kinds of behavior. What I'm saying, if I talk about gas exhibits two kind of behavior. Number first, if I talk about, is ideal behavior. It is what? It is ideal behavior. Okay, if I talk about the another behavior that the gas molecules exhibit, is the real behavior. Real behavior. Now, what is the basic difference between ideal and real? See, basically ideal refers to the hypothetical state or the fake state, I would say. In this state, we say that potential energy is zero. First of all, we say that potential energy is zero. Other than this, we say that ideal behavior is the state in which there is no interaction within the molecules. But you know, gases exhibit interactions. Yes, they do have interactions. They have forces of attraction, but very, very less. They have strong force of repulsion, but they have interaction. But it is saying that according to the ideal behavior, there is no interaction. So ideal behavior is the one which we are thinking, which we are assuming, which is the hypothetical one. So how would I define it? Hypothetical state in which there is no interaction within the molecules. Is it clear to you? Now students, in the upcoming segments, I'm going to tell you what is ideal gas equation, what do you mean by real gas. So we will discuss in detail. This is just an overview of what we are doing right now. Now come students, intermolecular forces. See, we have seen that two forces act upon the molecules, right? Now if I talk about the intermolecular forces are also further classified into two categories. Now what are these two categories? One are the polar interactions. Okay. If I talk about the second kind of interactions, that comes out to be the non-polar interactions. Which one? Non-polar interactions. Clear? Now, as the name suggests, polar refers to the one in which poles are made, in which charges are developed. And non-polar are the ones in which charges are not developed or charges are not involved. So I would write first of all here, charges develop or are made, right? And in this case, non-polar one, no charge development. That means no poles development. Okay, now if I am going to differentiate polar interactions into further three categories, they are classified as dipole-dipole interaction. Number first is dipole interactions. If I talk about the next one, students, that is dipole induced interactions. Dipole induced interactions. And if I talk about the third one, students, that is iron dipole interactions. Iron dipole interactions. Is it clear to you? Okay. Now students, if I talk about the non-polar interactions, I would say these are the dispersion forces or the London forces, right? So here we are going to talk about the dispersion forces. Now what I'm going to do, I'm going to tell you all of these in detail. Okay, now first of all, let us talk about dipole-dipole interaction. Dipole-dipole interaction. Okay. If I talk about dipole-dipole interaction, students, now what happens over here? See, dipole-dipole refers to the generation of charges that you need to keep in your mind, because it comes under the category of polar interactions. Now, second thing, students, let us take an example of HCl. Before understanding HCl, in general, if I would say there you have two atoms, A bonded with A. Now in this case, what happens? You have two same atoms. When there is two same atoms or similar atoms present, then there is no difference in the electronegativity. Now what do you mean by electronegativity? Electronegativity refers to the tendency to attract a shared pair of electron towards itself. And it only arises when there are different atoms, dissimilar atoms. In this case, if I would say this is the bond, it contains two electrons over here. This bond has two electrons and they are shared between them. There is no difference in the electronegativity because the atoms are similar. Clear? But if I ask you that if I have A and B, and there is a bond between A and B, and if there is a bond between A and B, and I would say you, if B is more electronegative than A, what would you say? You would say that if B is more electronegative than A, then B would attract electron towards itself. Right? Now, the attraction of electron doesn't refers to the breakage of bond. It means the pull of electron, the shifting of electron towards itself. Do remember this thing. You don't have to break the bond between them. You just have to pull the electron towards the atom which is more electronegative. So the atom which is more electronegative over here is B. So I would say these electrons are now shifted towards B. See, here they are present in between, but in this case where B is more electronegative, the electrons are shifted towards B. And when electrons move towards any of the atom, the species acquire negative charge. You know, an atom basically is a neutral molecule. It has equal positive and equal negative charge. Clear? Now, when whatever, if I would say negative charge, moves away from the neutral species, what charge it would develop, or what charge is left with the species? It would be left with positive because negative is moving. Same happens with A here. A basically used to have electrons with B, but now there is a shift of electron towards B. So A is now what? A is referred to as a positive charge species, while B, which is gaining electrons, which is having a pull of electron towards itself, will acquire a negative charge. Now the question arises, okay ma'am, it is clear that B will acquire negative and A will acquire positive. Do we write it as a partial positive charge or a full complete charge? See, when there is a breakage of bond, then the complete charges you are going to write positive +1 and -1. But when there is a shifting of electrons, or when there is you can see the pull of electrons and the bond is not being broken up, then you have to write the charges in the form of partial. It is going to be partial negative, it is going to be partial positive. This states that the bond is not being broken up. It is just there is a pull of electrons. Clear? Okay. Now let us see the dipole-dipole interaction. I would say this concept is going to help you a lot in this situation. How? If I talk about HCl. Now, there is a bond between hydrogen and chlorine, and there are two electrons in between them. Now, if there are two electrons in between them, what do we observe over here? We observe over here that chlorine is more electronegative as compared to hydrogen atom. When chlorine is more electronegative as compared to hydrogen atom, that means there is a shift of electron towards chlorine. There is a pull of electron towards chlorine, and when there is a pull of electron towards chlorine, chlorine will acquire which charge? Partial negative, and hydrogen will acquire which charge? Partial positive, because hydrogen now is being electron deficient. Electrons are moving apart from hydrogen, right? So if chlorine is more electronegative, so it will acquire partial negative and hydrogen will acquire partial positive. Now this is one dipole. This is my one dipole in which charges are developed. Now what happens? Dipole-dipole interaction refers to one dipole being interacted with another dipole. So here, what is my another dipole? Again, I am taking HCl case. Again, I know chlorine is more electronegative, so it will acquire partial negative charge. Hydrogen will acquire partial positive charge. So what do we observe over here? This is my first dipole, this is my second dipole. I observe that yes, the negative charge of this species is going to interact with the positive charge of the another species. This is known as force of attraction. This is force of attraction. Why force of attraction? Because negative species always attract positive one. You are never going to observe that negative and negative are approaching towards each other, or positive are approaching towards each other. They move far away from each other. Clear, students? So what do we observe over here? That one species negative charge is being attracted to the another species positive charge. Clear? This is referred to as dipole dipole interaction. Now comes the next kind, which is known as dipole induced interaction. See, when I talk about dipole induced interaction, now here you know that one is dipole, another one is induced. Induced refers to develop charge on the atom which doesn't have any charge. See what I'm telling you. Here in the first case, we had both of the species, both were dipoles, both generated charges on each other, and there was interaction between both of them. But in the next case, one of the species is polar, but another one is non-polar. That means one of the species is having charge on them, but the another one is not having. But what happens? We are showing interaction between both of these. Now the species which is having charge will generate charge, will induce charge on the one which is not having charge. Let us take one example. If I talk about water molecule over here, water molecule is basically H2O, and you know that oxygen is more electronegative, so it will acquire negative charge, while hydrogen is least electronegative, or I would say electropositive, acquires a positive charge. Now when it is approaching towards a xenon, let us take xenon. Now what happens? Xenon basically is a neutral species. Now when oxygen atom is approaching towards xenon, oxygen is negatively charged species. When it is approaching towards xenon, it will generate a positive and a negative charge on it. It will induce charges, but the charges will induce in such a way that xenon basically will have positive charge over here and negative charge over here. Why positive towards here and negative towards? That's why, because students, positive and negative attract each other, negative and negative repel each other. Positive negative attracting, negative negative repelling, and positive positive repelling. So this, if from this side positive was approaching, then the negative end would be this side, but from this side negative is approaching, so positive would come this side. Is it clear to you? Now in other words, you can also learn this in such a way. Dipole induced interaction in our general life, if I talk about, is the interaction. For example, your parents are your best motivator, right? So they are the charge that is developed on them. That means they are the full of motivation. They are, if you are sad, they are coming, they're approaching towards you, and they make you charged also. That means what? Dipole is inducing the other molecule to become a charged species. This is dipole induced interactions. Are you getting my point? Now students, moving to the third case over here, that is ion dipole interaction. What I'm talking about? I'm talking about the third one. It is ion dipole interaction. Now what do you mean by ion dipole interaction? See, in ion dipole interaction, one is dipole, this you got to know. One is ion. Now ion can be anion, it can be cation. Anion is the one which is negatively charged, cation is the one which is positively charged. So what happens? See, when a negatively charged species, for example an anion, approaches towards a dipole, at which end of the dipole it would approach? It would approach to the end which is oppositely charged. For example, if it is negatively charged, it will approach towards the positively charged first, positively end first. So this is the positive end of the species, this is the negative end. This is basically a dipole, let us say. Okay, now if I talk about cation, students, if I am talking about cation, it is a positively charged species. So at which end of the dipole will it approach? It will approach to the oppositely charged one. That means it will approach to the one which is having negative end towards itself first. So this, it will approach in this situation, right? Now let us take one more case to explain this also in detail. If I talk about a beaker, this beaker basically has water in it, water as solvent, and what happens? I am inserting NaCl. Now basically NaCl is an ionic species. If it is an ionic species, it has two ions, Na positive and Cl negative. And as you know, Na positive is cation and Cl negative is anion. So what will happen over in this case? Ion dipole interaction will occur. How come? If I talk about Na positive is the cation, right? Now a cation will attract which end towards it? Negative end towards it, right? Because positive and negative will attract, right? Now if it will attract the negative end in water molecule, you know that this is a dipole. Here, which is the negative end? Obviously oxygen is a negative end. So how it will show interaction? Let us see. Oxygen will show interaction first because oxygen is negatively charged. So this is the water molecule. like this. So interactions are shown such a way. These are negatively charged, so I'm writing negative charge over here. These were positively charged, so writing positively charged over here. Is it clear to you? Now, if I talk about the anionic portion, that is Cl negative. See, if I talk about Cl negative, which is an anion, which end of the dipole will come towards it? Positive end. Now, in the case of water, which is the positive end, we are talking about positive end is our H positive in case of water, right? So, H positive will approach towards it. It will look like this. Is it clear to you? Now, these were the negative ends, these were the negative ends, and these were the positive ones. So the positive ones approached towards the Cl negative. So this is basically what it is, ion dipole interaction. Is it clear to you? Now students, before moving towards, to the next topic, that is our non-polar interactions, let us talk about solvation. Let us talk about solvation. What do you refer to solvation? Basically, the thing which we did in the ion dipole interaction is the same, referred to as solvation. Solvation is basically the phenomena of generating charge, the phenomena of oppositely charged species and getting surrounded by the opposite end of the another one of the solvent molecule. Like the solvent molecule, if our species, if our ion is positively charged, the oppositely end of the solvent molecule, negative one, will approach towards it. If our, the ion is negatively charged, then the positive one of the solvent will approach towards it, just as we saw in the previous case. So solvation is basically the phenomena of ion to interact with the oppositely charged end of the solvent, or I would say dipole, right? Now, if I take solvent as water, it will be referred to as hydration. What do you mean by hydration? When the solvent is taken as water. Now, what do you mean by solvent? See, basically solution is comprised of two things. One is solute, another one is solvent, right? So solute is the one which is being dissolved, and solvent is the one in which the solute is being dissolved. Solute is the one which is in less amount, and solvent is the one which is in more amount. Is it clear to you? Now students, comes our next interaction, that are non-polar interaction, or I would say London or dispersion forces. Now, if I am talking about non-polar interactions, let me tell you, in these interactions, there is no, dipole development, no charges development, no poles development. So how come we can observe the interaction between them? See, if we say non-polar interaction, that means there is no interaction. Okay, when there is no interaction, students, then they would be gases. General case, when there is no interaction, when they are far more distant, then these are referred to as gases. But no, it is not true. Benzene is a liquid, but it comes under the category of non-polar interactions. But you told that non-polar are the ones which are gaseous only, because they are at a far more distance, as we have seen the assumption. Now this, how does in benzene these all cases arises? How does in benzene we see the interaction? So what happens over there is, we know that an atom contains basically a nucleus and an electrons. So the interactions occurs in such a way that the temporary dipoles are created. The electrons basically are attracted towards the nucleus of the another species in such a way that the electrons are moved to one end of the dipole, and the nucleus moved to the another end. So there is a temporary development of the temporary dipole is developed in between the molecules. Temporary dipole arises. Okay, now next, moving to the next category, that is hydrogen bonding. You should also know about hydrogen bonding, students. If I talk about hydrogen bonding, basically it arises when we have when we have fluorine, oxygen and nitrogen. What happens over here, all of these three atoms are basically have more electronegativity. So if I talk about water molecule, see water molecule is H2. Now here you see I take one more water molecule over here. What do we observe? We know that oxygen basically is a negatively charged species, hydrogen is a positively charged species. Oxygen is negatively while hydrogen is positively. Why oxygen is negative charge species? Because it is more electronegative. Now electronegativity refers to as the tendency to attract shared pair of electrons. Now this molecule's electronegative atom will make a bond with another molecule's electropositive atom, so there will be interaction in both of these. Now these interaction is known as H bonding, that means hydrogen bonding, and it is seen in the case of oxygen, fluorine and nitrogen making bond with another atoms, a more electropositive atom, right? So this was all about hydrogen bonds, students. Now comes the assumption for ideal gas. Now as I've already told you, a gas exhibit two kinds of behavior. One is the ideal behavior, another one is the real behavior. If I am telling you about the ideal gas behavior, the one thing I've already told you that it is a hypothetical state. Second thing I told you that there is no interaction between the molecules. So the very first assumption, why I'm writing assumption? Because it is a hypothetical situation. So assumption of ideal gas. Assumption of ideal gas. Okay, if I talk about the assumption of ideal gas, first of all, I've already told you there is no intermolecular, forces between the atoms. No intermolecular forces. Now students, if there are no intermolecular forces, that means there is no interaction. When there is no interaction, that means the molecules are at a far distance from each other. Hence, I can say that intermolecular distance is high. Intermolecular distance is high. Is it clear to you? Now students, coming to the next assumption of ideal gas, it is considered that the volume of molecule or the gaseous is very much less than the volume occupied by the container. So I would say the volume of the molecule or the gas is less than that of volume occupied by container, or volume of container, I would say. This is also the assumption for ideal gas. It is considered in such a way only. Now these molecules which are present in the container basically exhibit a random motion in a continuous motion or Brownian motion, I would say. These molecules move in random motion, random and continuous motion in a zigzag manner, okay? Now, other than this, these molecules usually what they do, they collide with themselves also and with the walls of container also. These molecules collide with themselves and also with the walls of container. The walls of container. Is it clear to you, students? So these were the assumptions of ideal gas, students. Now comes our next segment, that is going to be measurable properties of gases. Now what are the measurable properties of gases? See, we have already seen that about the intermolecular forces. Now there are certain state variables which defines us about the measurable properties also, which defines us about the physical state of gases. Now see what happens over here. Now the state variables, state variable defines us about the physical state of the matter. It can be pressure, it can be volume, it can be number of moles, it can be temperature. There are 4 state variables which we are going to talk about. Now, from these, which are the measurable ones which we can measure? One is first of all the temperature one. Temperature basically is the degree of hotness and coldness, right? Other than this, experimental studies have shown that absolute zero on Kelvin scale is equivalent to minus 273.15 degrees Celsius. That's why if you want to calculate, and if you're given a temperature in Kelvin or in Celsius and you want to establish a relationship between them, so this is your correct formula to calculate temperature in Kelvin is equals to temperature in Celsius plus 273.15. Clear? Now students, the next measurable property if I talk about is pressure. Now what do you mean by pressure? Pressure basically refers to the force acting per unit area. These all things we have already covered in our small classes, you know. Now it is basically, it is a re-revision for you, right? Now see what happens over here. If I talk about the pressure on a gas, according to the laws of motion, pressure is defined as the force applied per unit area of surface. Now pressure is equals to force by area. This is the formula that we are going to use in many of the questions, right? Other than this, unit is given to you, that is Newton per meter square or Pascal. And if you are given like the pressure unit is also an ATM now. So if you want to, they have given you to convert ATM into basically mm of Hg, which is also a unit of pressure, I would say 1 ATM is equals to 760 mm of Hg. This is your first conversion. Now if I talk about the second conversion, if you need to convert into centimeter of Hg, it will be 1 ATM is equals to 76 centimeter of Hg. Clear? And if you want to convert it into torr, it will be 1 ATM is equals to 760 torr. Other than this, you can also convert it into bar. It will be equal to 1.01 approx something. Clear? So these are basically the units of pressure, and you do the units conversion as well. Now comes atmospheric pressure. What do you mean by atmospheric pressure? The actual value of atmospheric pressure basically, students, depends upon the temperature, location and the weather. And whenever you need to calculate the atmospheric pressure, you need an instrument known as this barometer. Now this is the basic thing that you need to know as a general knowledge. Now moving to the next segment, that is going to be gaseous law. In the previous also, when I'm talking about the measurable properties, students, one of the measurable properties that is left over there is volume, which we will consider in these segments, so don't worry about it. Right, now comes the most important segment of states of matter. In these topics, each and everything, I want you all to write separately on a sheet and paste it on your cupboard or wherever you study, in your study room, because from here you are going to find out the numerical portion also. You are going to calculate the questions also. Like 80% of the work is we are going to do in these upcoming segments. Clear? So if I talk about gaseous law, what are the gaseous law? The laws which establishes a relationship between the state variables, that means pressure, volume, temperature, number of moles. So when we are going to establish a relationship between these state variables, these laws are referred to as gaseous laws. Is it clear to you? Now moving to the very first law is Boyle's law. What do you mean by Boyle's law? See, what we are going to do is, we know that basically there are 4 state variables: pressure, volume, temperature, and we have number of moles. So what we are going to do is, we are going to establish a relationship between 2, and one is kept as a constant, and another one also, like in most of the cases you are going to see that n, that is the amount of gas, number of moles, is almost constant. In many of the cases there will be case when it is not constant, so I'll consider that. So keeping this n aside, I would say that from these 3, pressure, volume and temperature, we are going to see a relationship where one is kept as a constant and other 2 are being found with a relationship. Now let us see for the Boyle's law. If I talk about the Boyle's law, here for a particular amount of gas, kindly listen to this line very carefully. For a particular amount of gas, or a given amount of gas, I would say particular or a given amount of gas, what this lines state us, this state us that, what do you mean by amount of gas? It is number of moles. That means here you are keeping number of moles as constant, right? So other than number of moles, we have to establish relationship. So here number of moles are kept as constant. Now to establish relationship, what we are going to keep here as a constant? We are going to keep here temperature as constant. See, this is already kept as a constant, this we have also kept as constant. Now we will establish a relationship between whom? Pressure and volume. So here for a given amount or a particular amount of gas, when temperature is kept constant, when temperature is kept constant, pressure is inversely proportional to volume. volume of gas. Now this is Boyle's law. What I have said that for a given amount of gas, that means N's value is constant. When temperature is constant, when T is constant, then the pressure will be inversely proportional to the volume. In other words, I would say pressure inversely proportional to volume. Now to get rid of this proportionality sign, I would introduce a proportionality factor, which is K. So I would say pressure is equals to K into 1 by V. K here refers to proportionality constant. Is it clear to you? Now students, the most important portion over here, we have derived one formula. Pressure is equals to K into 1 by V. Okay, now kindly tell me, if I take 1 by V on the another side, it will be multiplied, right? So what is the value of K from this? We get that K is equals to P into V. Now see, there are some cases when they will give you in the question paper that you have two stages. In these two stages, what do you observe? For example, this is your first container, this is your second container. Now for the first container, the pressure comes out to be 1 atm and the volume comes out to be 2 liter. Okay. Now if I talk about the second one, if I add some volume over here, the volume become 5 liters. And kindly calculate pressure when temperature is kept constant. So which law you will apply? You will apply Boyle's law. But how will you do this? You know that firstly you are given with pressure and volume, and in the second situation you are only given with the volume. So you can derive this formula from here. When you know that K constant is equals to P into V, now for the very first state I can write this, that constant is equals to P1 into V1. K remains as a constant because it is proportionality constant, right? Now if I talk about the second case, K will equal to P2 into V2 as well. Now students, if I compare this first and second equation, comparing 1 and 2. When I compare 1 and 2, what I am getting? P1 V1 is equals to P2 V2. Kindly put a star mark over here because you are going to get a lot of questions from this formula. Clear? It will be applied only when temperature is kept constant. Clear? Other than this, students, if I ask you to draw a graph between pressure and 1 by V. See, you know that pressure is equals to K into 1 by V. So we can write it as Y is equals to mx plus C. Now students, here kindly observe very carefully. Here on y-axis we are writing pressure, on x-axis we are writing 1 by V. On slope, m refers to as slope. What is slope? Slope is K. And from where does slope will arise? See, here C value comes out to be 0. That means slope will arise from origin. If C has something as a value, then it would, cut on the y-axis. But if C value is nothing, then the slope will arise from the origin. So this comes out to be our line. So it comes out to be a straight line when the graph is plotted between pressure and 1 by V. So this is our slope. Slope is m equals to K. Is it clear to you? Now students, we are going to see one more graph for Boyle's law. If I ask you, now this was the graph between pressure and 1 by V, which came out to be this. If I say draw a graph between pressure and volume, not with 1 by V, how will you make it? See, you clearly know that pressure is equals to K into 1 by V. If I am going to increase the volume, pressure is going to decrease. Or if I am going to decrease the volume, pressure is going to increase because they are inversely proportional. So all I would say is, if V is equals to 0, pressure would be equal to infinity. Do you agree with this? Right. If V is equals to infinity, pressure is going to be 0. So we are going to get this, we are going to get this hyperbola curve over here, and this is referred to as an isothermal situation. Now what do you mean by isothermal situation? Iso refers to same, that means constant. It refers to same, or I would say constant. And thermal refers to what? Thermal refers to temperature. So when you observe a graph on same temperature, that means we are obtaining a graph between pressure and volume, because from the three variables, when one is kept as a constant, the relationship is established from the other two. So this is known as isothermal graph. Now students, if I ask you one more question over here, if I say I have graph between pressure and 1 by V, and these are my lines on a particular amount of temperature. If I am going to say this is the line I obtained when temperature is T1, this is the line obtained when T2, and this is the line when obtained T3. Now kindly tell me which will have more temperature, which of the following is more temperature. You will say that, ma'am, it is quite simple. How it is quite simple? We know that pressure is equals to K into 1 by V. Also students, let me introduce you to one equation which is referred to as ideal gas equation. What is that equation? It is PV is equals to nRT. Okay. Now, if I take this volume here below, because I want to establish a relationship between pressure and volume, so what will come out to be here? Pressure is equals to nRT into 1 by V. Clear? Now here you know that N is constant, R basically is gas constant, and T is also constant because it is isothermal. So we can replace it with K because these are constant. So here what does K comes out to be? K comes out to be nRT. That means K is directly proportional to temperature. Right? Now what was K? We have already done in the previous situation that K basically is the slope. K basically is the slope. So what you are seeing, more the temperature, more will be the slope. Now more will be the slope refers to the more angle, right? Now this has more slope, this one, this situation. That means here K value is more. If here K value is more, then temperature value is also more because it is directly proportional. So here T1 is more than T2 than is T3. So such kind of question can be arised from the graphical section, students. Okay, now this ends our first law. Now comes our second law, that is the Charles law. If I talk about the Charles law, here also we are going to keep one of the thing constant. First of all, let us write that for a given amount of gas, for given amount of gas, what we are going to see. Now when I am talking about a given amount of gas, I am talking about the value of N, which is kept as constant. Now from pressure, volume and temperature, which thing we are going to keep constant? We are going to keep here pressure as constant. When pressure is kept constant, when pressure is kept constant, then volume is directly proportional to temperature. To what? To temperature. In the previous case, pressure was inversely proportional to volume, but here volume is directly proportional to temperature. So this is a different kind of situation. Do not get confused between both of these because these laws are very important. Now students, let us see. I am saying volume is directly proportional to temperature. Now to get rid of this directly proportional side, I am going to dictate it. I am going to write a proportionality constant which comes out to be K. So I am getting V is equals to KT, right? Now students, if I want one more thing, if I want what that, if I'm going to take this K over here or this T over here, I'm getting V by T is equals to K. Now if I'm getting V by T is equals to K for two of the situations, what I'm going to write, just I have done in the case of the previous, I have done P1 V1 is equals to P2 V2. What I'm getting from here, I can write that for first situation V1 by T1 is equals to K, and for second situation V2 by T2 is equals to K. Now comparing both of these, what I am going to get over here, that V1 by T1 is equals to V2 by T2. Now again you have been given a formula that is going to help you in the question parts, right? Do not forget this formula. In the previous case we got to know P1 V1 is equals to P2 V2. Here we are getting V1 by T1 is equals to P1 V1 is equals to P2 V2, and in this case we are writing V1 by T1 is equals to V2 T2. Now if I am going to draw a graph, the graph between volume and temperature, see here V is equals to K into T. So I can again write Y is equals to mx plus C. Now here C is also 0. So here it will arise, and you know that it is directly dependent upon temperature. So this is also a straight line, but it is quite different from the previous one, because in the previous one we got to know about the straight line, in which case when the relation was established between pressure and 1 by V. But here the relationship is established between what? Between volume and our temperature. Now here also, if I ask you one general question of the graphical section only, students, if I say you there is a graph between volume and temperature, and you have these as your particular lines, this, let us say this is the line for P1, this is the line for P2. Which is more? Is P1 more or is P2 more? So all you would say is that, ma'am, it is quite simple. We know that volume is equals to K into T, and we know that PV is equals to nRT according to the ideal gas equation, and we want to establish a relationship between volume and temperature. So pressure will come down. What will come? Volume is equals to nRT by P. Right now, students, I know that in this case, in Charles' law, pressure is kept constant. So this is constant, R is constant, N is constant. We can replace it by K. Hence, K comes out to be nRT by P. Or I would say that K is inversely proportional to pressure. Now, in the previous case, we saw that K was directly proportional to temperature. But here, K is inversely proportional to pressure. So here, more the pressure, less will be the slope. We need to find which pressure is more. Whose slope is less? This slope is less, so its pressure is more. So P2 is more than P1. So see, it rolls up the situation. In the previous situation it was almost different, in this situation it is almost different. It only depends upon the K. That K depends on pressure, how much directly or indirectly. Is it clear to you? Now students, moving to the this portion only, if I talk about when we take temperature in different terms, as I've told you, we take temperature in Celsius and Kelvin. If I take temperature in different terms, all I would say is that volume basically will be equal to what? We know that volume is equals to K into T. And now when I am taking this, volume is equals to K. Now T plus 273. Okay. Now this is in 273. Clear? Now if I am taking that, V is equals to K into T. Now the temperature, basically I have changed my temperature, this. Clear? Now this I have written, you can either write it inside or outside, it is the same thing, it is the unit, it is the Kelvin, right? Now if I open up, what I'm going to get, V is equals to KT plus 273. Now students, see, Y is equals to mx plus C. It is the same thing, y is equals to mx plus C. Now if I am going to draw a graph over here, now C has some value 273. C has some value 273. So the intercept will start from this direction. And when I extend this graph over here, students, it will cut over here, and this is known as absolute temperature. This is known as absolute temperature. So this is the plot when temperature is taken in Celsius. Okay, so when you can see that in Celsius or Kelvin, we get different graphs. I have given you the formula. If you are given the temperature in Kelvin and Celsius, you can directly write that when Kelvin is equals to, in the previous case, let me show you once again. Let me open up. When we were studying the measurable properties, students, see here, when we were talking about, sorry, it ran far away, right? Okay, wait a minute. See here, when it was given in Kelvin, and when you need to calculate in Kelvin, you're given Celsius, then you add 273.15. Same here situation arised, we have added directly 273, right? We have added directly 273. So here you have got this answer in Kelvin, so I have written Kelvin outside that. So I have written Kelvin outside that. So if you are finding out this in Kelvin, sorry I told you Celsius, if you are finding out this in Kelvin, then you can obtain this kind of graph, and here at which it is cutting, it is minus 273 Kelvin. Is it clear to you, students? Now this was all about our second law, about Charles' law. Now moving forward towards the third law, that is the Gay-Lussac's law. Now what happens over here? See, we have done a situation where we have said that pressure is kept constant, temperature is kept constant. Now one of the things which is not kept constant will come over here, and that is volume. So here what we are going to do for for a given amount of gas, Again, n is constant. So for a given amount of gas, when volume is kept constant, when volume is kept constant, then pressure is directly proportional to temperature. Okay, now what happens over here? I want you all to write this equation. Till then, I'll drink a glass of water, right? Kindly write this situation super fast. Okay. So here, what I have told you, we are going to keep one of the state variable as a constant and finding the relation between the other two. So we have to find a relationship between the other two. What are the other two? Pressure as well as temperature, which are directly proportional. So I can write pressure is directly proportional to temperature. Is it clear? This thing is clear to you now, students. To get rid of this directly proportional sign, we introduce k. Pressure is equals to k into t. You know this very carefully, very nicely. Now, what is the value of k over here? If I say k comes out to be pressure by temperature. Now, for two situations again, k can be equal to P1 by T1, and for the another state it will be equal to P2 by T2. So what will be the formula that we are going to derive from here? P1 by T1 is equals to P2 by T2. Is it clear to you? Is it clear to you? Again, put a star mark over here because it is going to help you in the numerical section. Okay, now let us plot a graph of pressure and temperature. Okay. If I'm going to take temperature on x-axis and pressure on the y-axis, what I'm observing over here, that pressure is equals to K into temperature, which is equals to Y is equals to mx plus C. Again, C here comes out to be 0. That means the line is going to come out from here. The slope is going to originate from the origin itself. So is it clear to you this state? Now students, other than this, we are going to plot a graph just similar to the previous situations. How come? See, if I say you have been given three states, this is pressure, this is temperature, again you have been given these three slopes over here. Let us say the first one is v1, the second one is v2, and the third one is v3. Which one is more? So again you will say that let us compare it to the ideal gas equation. We would say that here PV is equals to nRT, and we are establishing a relationship between pressure and temperature. So let us take volume on the another side, that is nRT by V. Now if I see comparing the P is equals to KT, here K comes out to be nR by V. Hence I can say that K is inversely proportional to volume. More the volume, less the slope. More the volume, less the slope. This will have more volume because the slope is less. When there is slope less, there is more volume. When there is slope more, less volume, so it will have less volume, so more volume will be v3 than v2 than v1. So these three basically laws have most important question on the graphs, which I have already covered here. Now students, comes out our next law, which is Avogadro's law, which is the last law. See here, if I talk about the three state variables, we have already covered the three state variables about pressure, about volume, about temperature. Now comes the Avogadro's law. In Avogadro's law, we are now going to state about number of moles. What we are going to say? We are going to say that at constant pressure and temperature, at constant pressure and temperature, students, and temperature, volume is directly proportional to number of moles. It is directly proportional to to number of moles. Just like this. V is directly proportional to N. Now to get rid of this directly proportional sign, we will introduce proportionality constant, which is K. So V is equals to K into N. Is it clear to you? Now we will plot a graph between volume and number of moles. So the graph comes out to be straight line. How come? Because volume is equals to K into N, which is equals to Y is equals to mx plus C, where C comes out to be 0, hence originating from this origin point. Is it clear to you? It is quite simple, students. Yes? Okay. Now let us see about ideal gas equation. To derive ideal gas equation, first of all, write 4 laws which we have studied. The very first law, which was Boyle's law, came out to be pressure is inversely proportional to volume. This was Boyle's law. Okay. Now let us talk about the second law. Which was second law? Charles' law. In Charles' law, pressure was kept constant, so volume was directly proportional to temperature. Okay, if I talk about the next one, the third one, that was Gay-Lussac's law. Here, what do we observe? The volume was kept constant, so pressure was directly proportional to temperature. And the last one, which is studied just right now, came out to be that volume is directly proportional to number of moles. We studied in Avogadro's law. Right? Now, students, comparing all of these fours, what we are going to do? We are going to compare these four. Now, when we compare these four, students, what we get over here, kindly see. Pressure basically is directly inversely proportional to volume and directly proportional to temperature. So what do we see here? That PV is directly proportional to, one second. PV is directly proportional to N into T. See, how come? Pressure is directly proportional to temperature, right? Volume is directly proportional to number of moles, right? Volume is directly proportional to temperature, this is also right. And you know that pressure and volume are inversely proportional, so they are written together. Because if you take this on this side, then it is going to be PV, right? So here, to get rid of this directly proportionate sign, we are going to introduce the gas constant, because it is the ideal gas equation. So it comes out to be PV is equals to nRT. Now this is going to be our ideal gas equation. This is going to solve your most of the questions. See, these four formulas are basically very, very important. What were these formulas? Let me write over here all of the formulas. P1 V1 is equals to P2 V2. The next formula was V1 by T1 is equals to V2 by T2. Now the next one was P1 by T1 is equals to P2 by T2. Clear? Now the fourth one, PV is equals to nRT. Okay, students, now we can write one more formula from the situation over here, that P1 V1 by T1 is equals to P2 V2 by T2. Now this is also the formula that is going to help you out in most of the questions. You are going to practice and you are going to see all of these formula in your numerical section. So I've just sorted all the formula portion over here for you to write. You can directly make a page and write it on the sheet and put it on a cupboard or in your kitchen. Right, students? Okay. Now this ends our ideal gas equation and we are moving forward towards our next segment, that is Dalton's law of partial pressure. What do you mean by Dalton's law of partial pressure? When two or more than two non-reacting gases are mixed in a container, they tend to behave individually. Now what I'm going to say here is, see, if I have taken a big container and it is being parted in such a way that in the first portion is a gas which has a pressure of Pa, and in the second container, in the second part, it has B gas which has a pressure B. Now if I'm going to ask you what is the value for the total pressure, you would say, ma'am, the total pressure will be sum of both of these situations. So we can say that the total pressure is going to be Pa plus Pb. Is it clear to you? Is this situation clear to you? Now we know, according to the ideal gas situation, what was our formula? PV is equals to nRT. Okay, now for individually, you can write for both of these, for PA as well as for PB. So what you are going to write for them individually? PA is going to be PA into V is equals to be NA into R into T, because volume, gas constant and temperature will remain constant over here, right? Now for the next one, PBV is equals to NBRT. Okay, now if I would say from this first and second situation, kindly find out PA and PB. So you would say from equation 1, PA comes out to be NART by V, right? I took the volume and on inside in means below this situation, and from equation 2, what do we get? PB is equals to NBRT by V. Is it clear to you? From first and second situation, we have done this very easily. Now, what is the next step over here? We have to equate both of these in the total pressure one. When I'm equating both of these over here, let us say this is your equation number 3. And let us say this is your 4th and this is your 5. Okay, now I'm writing, put 4th equation and 5th equation in equation number 3rd. So what you are getting over here is PT comes out to be NART by V plus NBRT by V. Now students, V. If I talk about PT, what is PT? The total pressure. Now total pressure will have, total number of moles, so I can represent it by NT. When I am going to represent it by NT, it comes out to be NTR. NT, that refers to the total number of moles. Okay, that means the sum of them, divided by V, it comes out to be equal to NART by V plus NBRT by V. Is it clear? Now let us take the things which are common over here. If I find out what are common, I find out RT and V are common. So what I'm going to do, I'm going to take common. Here RT by V will come out common, and inside will be only left Na plus Nb. So this will be cut from here and here, and we obtain that total number of moles will be equal to the individual sum of the moles, right? This is also going to help you from the Dalton's law of partial pressure. Other than this, we need to calculate one more formula, students. Now here, if you see, I'm going to write these again here. Okay, now you know that PA is equals to NART by V. We have already seen this. And PB is equals to NBRT by V. This also we have seen this. Okay. Now if I talk about the total pressure, it will be PT. It is equals to what? NTRT by V. Yes. Okay. Now give them numbers also. Let us say this is your 6th, this is your 7th, and this is your 8th, right? Now let us say divide 6 by 8 or 7 by 8. It is the same thing. You need to derive both of the formulas. So I am dividing 6 and 8. See what I'm going to get. PA is equals to NART by V. I'm going to divide it by PT is equals to NTRT by V. See, RT by V is cancelled out. What I'm getting from here, PA is equals to NA. And under this we have PT, under this we have NT. Now what do you mean by Na and NT? Na refers to number of moles of A, NT refers to total moles. Whenever you are dividing the particular moles of a substance by the total moles of a substance, it comes out to be mole fraction. So it is equivalent to what? Mole fraction of A. It is equivalent to mole fraction of A. Now all I would say is here is PA by PT will be equivalent to mole fraction of A. This is the important formula, or I would say this is the important formula that you need to keep in your mind. Now students, I can take this PT on the another side. I can cross multiply this, right? So what I will get from here, PA is equals to mole fraction of A into PT. This is the important thing that we have been calculating in the Dalton's law of partial pressure. Now similarly, I can calculate for PB. PB is equals to mole fraction of B into total pressure. See, now what are P and PB? P and PB are the partial pressures that were present in the container that I have showed you previously, right? Now, if I ask you the total pressure, what is the total pressure? It is sum of the partial pressures, then you will get this. Then you can directly write this here, that total pressure, you can take this on the other side, you can directly write the total pressure is the sum of the partial pressures, that is the P naught A plus P naught B, right students? And if I talk about individually, if I need to calculate between the relationship between PA and PT, then I'm going to use this formula. Then I'm going to apply this formula, that PA and PB basically is equals to the mole fraction into the total pressure. Is it clear to you? Okay students, now moving forward towards our next segment, that comes out to be Gram's law of diffusion, kindly mentioned in the Dalton's law. Yes, do remember which formulas they can ask you. Okay, here this formula is important to you. Very sorry. Okay, this formula is quite important for you to understand, because the question can be asked over here. Other than this, they can ask you this, and this. That's it. That's it. Okay. Now, students, moving forward towards the next segment, it comes out to be Graham's law of diffusion. I'm talking about Graham's law of diffusion. Now, what do you mean by Graham's law of diffusion? Basically, diffusion, first of all, let us understand about diffusion. Diffusion is a process of intermixing of gas molecules. When gas molecules diffuses out, moves out in the every direction. So, let us take one example to understand it a bit more. For example, you have this case, and you were having a membrane, first of all, over here. There was one, A type of particles here and B type of particles. Now what happened? If I remove this, whole surface, then what will happen? They will get intermixed. This is what a diffusion looks like. But if I talk about effusion, what will be effusion? See, there was a full, membrane over here that got removed and it got intermixed. But if I'm talking about effusion, in the case of effusion, we see that basically, sorry for the diagram. Okay. In this, we see that if this membrane had a small hole, then the particles movement from this small hole would be effusion. For example, a spray, I would say, the little movement of the particles in the air. When there is a complete intermixing of particles, that is diffusion. When there is a little movement from a particular hole, it is effusion. Now, students, come the most important part, that is the rate of diffusion, with the speed through which the particles move. Okay. So, if I talk about the rate of diffusion, students, rate of diffusion basically depends upon the pressure. It directly depends upon the pressure. It also depends upon the molar mass in such a way that it indirectly, that means inversely. So I would say rate of diffusion inversely depends upon the square root of the molar mass. Here m refers to the molar mass. Now students, if I am going to make a relationship between both of these coming together, what I am going to find is that rate of diffusion is, equal to what? Pressure divided by, a square root of molar mass. Here it is directly proportional. So kindly put that mark. Okay. Now for two of the situations, what formula can you develop over here for two rate? You can write that R1 by R2 is equals to P1 by P2 into root of M2 by M1. This is the formula that you are going to use, and yes, in your DPP section, student, in your DPP section, you are going to get a lot of questions from this formula. So put this formula also in your formula sheet. Kindly develop a formula sheet for physical chemistry. It would help you a lot. So whenever you are practicing question, you don't have to practice all the concepts. You just have to take your formula sheet in front of you, revise it out and apply it on the questions. So do put this also in your formula sheet. Is it clear? Now we can also define rate of diffusion in other terms. What are the other terms? If I talk about number of moles, so I would say rate of diffusion is basically equal to number of moles escaped, divided by time taken. Okay, now we can also define in the terms of volume. So we can say that rate of diffusion basically is equal to the volume change, like how much it traveled from one to another. So we can also calculate with the help of volume change. So volume change by time taken. Or if you want to apply the rate of diffusion in terms of pressure, students, you can say the pressure, the pressure dropped from first initial state to the final state. So the formula will be rate of diffusion is equal to pressure dropped upon time taken. Is it clear? Okay, and with the help of distance also you can even calculate rate of diffusion, that is distance traveled by time taken. Clear? So this was all about diffusion segment, students. Now we will move forward towards the next topic. Sorry, towards the next topic that comes out to be kinetic theory of gases. Now see, kinetic theory of gases is quite important for you to understand. It is quite simple also. First of all, the postulate of kinetic theory of gases are as follows. This we have already done. It is the ideal gas situations, right? So the gaseous molecules are considered to be point masses, just similar to the ideal gas we said. In ideal gas we told that the volume of the molecule, that means the volume of the gas is, very very less than the volume of container. Same is written here. See, the volume of a molecule is negligible as compared to the total volume of gas. Is it clear to you? Okay. The next point, you can see the molecules neither attract nor repel each other. Clear? The collisions that occur between the molecule are perfectly elastic. This is also a good point for you to understand. Now, what do you mean by perfectly elastic? That there is no loss of energy during the molecular collisions, during the collision time. Clear? Other than this, students, you have the average kinetic energy of molecule is directly proportional to the absolute temperature of gas. This is also important, so I'm mentioning over here. The average kinetic energy of the molecule is directly proportional to the absolute temperature of the gas. And the last one is the effect of gravity on molecular motion is negligible. Is it clear to you? So these points I have marked which are important. You can also highlight them. Now students, comes our the calculation for the kinetic theory of gases. Now, as we have done in the ideal gas equation, the formula was PV is equals to nRT. Now, for kinetic gas equation or kinetic theory of gases, I would say PV basically is equals to 1 by 3. Now see, there we used to say PV is equals to nRT. Here we are going to say PV is equals to 1 by 3 N, that means number of molecules, into M, that is the mass, into V square RMS, that is the root mean square velocity. Clear? Let us write all of these things here. V RMS refers to as root mean square velocity. Other than this, this is pressure, this is volume, and here is number of molecules, and here is number of molecules. Okay, if I talk about mass, mass is M. Here is mass of one molecule. M refers to the mass of one molecule. Is it clear to you? Is it clear to you, students? Okay, now if I talk about the kinetic energy, of one molecule, it will be half mv square. And if I say you there is a container, it contains, particles which have different velocities. So what will be the kinetic energy for that case? It will be half m1 v1 square plus half m2. Okay, half I'm taking as a constant, so m2 v2 square and so on. It is just like that for the different cases. Half m3 v3 square similarly. Now students, if I talk about root mean square velocity, if I talk about V root mean square velocity. It comes out to be v1 square plus v2 square plus v3 square plus v4 square divided by total number of moles, total number of molecules, that is n. Now here students, what you need to know here is this. See here in the kinetic energy, when we are talking about a single molecule, we say half mv square. Here v square is written, but for different cases this value is equal to v square. It is equal to v square, so we can replace v square as v square rms into n. Into this situation we can write it as, so we will write average kinetic energy comes out to be half into m. Now v square is replaced by this, we will cross multiply v square rms into n. This is what, this is our average kinetic energy. Now students, we have calculated this formula, but I have already told you this formula is still with us. This formula is still with us. PV is equals to, see, PV is equals to 1 by 3 n m square v square r ms. We have this formula with us. We have this state with us. Now see, you can, what you can do over here is you can replace this n m square, you know, this n, sorry, m square I've written, it is m, sorry for this. Here m will come, not m square, right? Now what you have to do is you have to replace n m into v square rms. Now take this 3 on the another side, it will be 3 pv, it will be 3 pv. 3 pv is equals to n m v square rms. Kindly put all of this here. Here what you get, you will get average kinetic energy comes out to be half into 3 pv, that means 3 pv by 2. This is the most important thing. This is the most important thing. Clear? We have calculated average kinetic as 3 by 2 pv. Is it clear to you? Now we know that students, that PV is equals to nRT, and for 1 mole, we know that PV is equals to nRT. For 1 mole n is equals to 1, then PV is equals to RT, so I can replace it over here. So average kinetic energy can be calculated as 3 by 2 RT also. It can be calculated by 3 by T RT also. Is it clear to you? So these were the formula that you need to keep in your mind while solving these questions. If you want to calculate number of molecules, then you will divide it by Avogadro number Na. Is it clear? Okay. Now students, moving to the next topic, that is molecular speeds in gases. Now there are 3 kinds of speeds in gases which we observe. One is the root mean square, which I've already told you, which is represented by VRMS, right? The second one comes out to be the average speed, which we used to calculate in physics also, right? You have done a lot of questions in your previous standard. And the third is most probable speed. Now if I want you all to just, you need to understand the formulas, that's it. For root mean square, the formula comes out to be, it is equals to root of 3RT by m. This is the formula for root mean square. Now if I talk about average speed, students, it comes out to be, here root 8RT will come. See here 3RT was coming, here root 8RT will come, divided by pi into m. Divided by pi into m. Clear? Now comes the last one, which is the most probable speed. It is quite easy. It is root 2RT by m. Is it clear to you, students? These were the molecular speed. So now students, comes the most important part of our lecture, that is behavior of real gas. We have done ideal gas in detail. We have done all the concept, all the laws regarding the ideal gas equation, Dalton's law, Graham's law of diffusion. Now students, come the behavior of real gas. So as I've already told you, there were a difference between ideal and real. Ideal was a hypothetical state, while real was a real state in which there is interaction. So the assumption of ideal gas says us that there were 2 things that were involved which were quite different from the real ones of the ideal ones. Now what are the different things? First of all, we told that the volume, the first thing that we told, that the volume was of gas molecules was very less. This was the assumption that was done, than the volume of container. And the students, the next thing that was assumed, that there is no interaction between the molecules. These were the assumptions that were already told. Now, let us see in the real gases what happens over here. In the real gases, what we are going to observe, right? So, for in the real gases, students, first of all, you need to know there is a compressibility factor which is represented by Z, which is represented by Z. Z for the ideal gas equation comes out to be 1. Z comes out to be 1 for ideal gas equation. Now, what was ideal gas equation? Let me tell you again. Ideal gas equation came out to be PV is equals to nRT. But yes, if I am introducing this compressibility factor, the equation came out to be PV is equals to Z into nRT. Now, if Z is 1, then the equation became PV is equals to nRT. But for real gas, students, this didn't have the same equation. For real gas, Z is not equal to 1. Now, there is a basic difference. I am seeing the behavior of real gas. These two things we will see will be different. These are the things we have seen in the ideal one, right? And these are the things that differentiates the ideal one and the real one. Now one comes the graphical portion here that you have to understand. There is a graph between compressibility factor and pressure. Okay, this is the compressibility factor Z and there is the pressure P. Now, as I have told you, for the, ideal gas equation, all of these have the value of Z as 1. Now, if I take, if I take gas H2, the line comes out to be this. When I take helium, the line comes out to be this. But when Z value, that means compressibility value is less than 1. What are the gases who have the compressibility value less than Z? They are NH3, they are CH4, these are CH4. So they have the value of Z less than 1. This basically is the line when the Z value is more than 1, this is less than 1. So here what conclusion we need to find over here, that when there is force of attraction, the value will be lower minima. See how? If I talk about NH3, we know that nitrogen exhibit hydrogen bonding. That means there will be force of attraction. So if it has force of attraction, the value will be lower minima. The curves come out to be lower minima. If the force of attraction decreases, the curves become the higher minima. Clear? So why this lower minima is arising over here? Because force of attraction has arisen over here. It is easy for you to understand. Now if I say less the kinetic energy, less the temperature, the gas will be easy to liquefy. So this is all I guess you will be seeing in this graph. The one thing that you need to keep in your mind, why this graph is coming like this, because in these cases interaction is occurring. That's why. Okay, now students, now comes our next part. If I talk about the next part, I will differentiate real gas and ideal gas so that it is quite easy for you to understand in the 4 basic steps. See, I am writing over here real gas. Here we will write ideal gas. See, if I talk about real gas or ideal gas is the one in which PV is equals to nRT. This is the situation, right? But here PV is not equals to nRT. We are going to find out what will be the formula for the real gas one right after this segment. Now see, the next one is that here in real gas, it can behave like a ideal gas but at low pressure. It is not equal to nRT, but at low pressure, students, it can behave. At low pressure, it can be PV is equals to nRT, but not like that. Not at the normal situations. Now, other than this, students, there is no force of attraction in the ideal gas because it is a hypothetical case. Here, there is no force of attraction. And here, yes, there is forces of interaction. Other than this, students, here if I talk about the ideal gas one, Z comes out to be 1. Here Z comes out not to be 1. Clear? So these are the things that we have already calculated. 1 second. I have to put a line over here. Okay, this is the difference between the real gas and the ideal gas. One more thing that you can observe, if I talk about the graph of real gas and ideal gas of PV. See, we have seen this was the graph for ideal gas. But if I talk about the real gas one, students, the graph comes out to be this. This is for the real gas. all of these depends upon the compressibility factor. For this it is not equal to 1, for this is equal to 1. Is it clear? Okay. Now students, moving to the next part is our equation. What is the equation for real gas? The question arises. The equation for real gas, as I've told you, it is not equals to PV is not equals to nRT. So what will be equal to nRT? P plus AN square by V square. This is the pressure correction term into V minus NB. This is the volume correction term. This is equals to nRT. See, now let us compare it with ideal one. Ideal says that P is equals to PV is equals to nRT. See here, we have replaced pressure with pressure plus AN square by V square, and we have replaced volume with V minus NB. Clear students? A and B here are constants. Now what is this and what is this? This is basically pressure correction. This is basically pressure correction. And this is basically volume correction. Why are we doing this pressure correction and volume correction? Because students, in ideal gas situation, he told us that volume of gas is almost negligible as compared to volume of container, students. But in this case in real gas, what do we observe? We observe that the particles are rigid. If the particles are rigid, that means they take some area and they need to be compressed. To need to be compressibility factor, we need to require a pressure, and moreover, when the particles are rigid, they will acquire a lot of surface, they will have some volume. When they have some volume, that means the volume doesn't comes out to be the volume V, it comes out to be different. The volume comes out to be different. See, now one by one I'm going to explain you. As I've told you, in ideal gas the particles were very little. Now see students, if I talk about actual volume of gas, first of all we are going to do volume correction. See, in volume correction, if I ask if I ask you about actual volume of gas, so it comes out to be what? Volume minus NB. How come? How come it comes like this? See, first of all, the actual volume, this is for gas for 1 mole, for N moles. Okay, I am asking the actual volume of gas. The actual volume that, firstly, initially the volume was V. Now it is being subtracted by B. Why it is being subtracted by B, students? Because in ideal gas, we said that the particle, for example, this is the volume of the container, right? When we gather all these molecules together, what do we get? When we gather them, these acquire only this much area. That means the rest of the area is the volume of container, and we told the volume of gas is very less than the volume of container, than this area. Right? Now this was not true. This was not true. In real gas, we observed that these molecules are big in size. When they are big in size, then we can see that. Then we can calculate their volume. Now we can calculate their volume because they are rigid. They are big in the real gas state. Now if they are big in the real gas state, then to calculate it, we need to subtract the volume of the gas to calculate the actual volume. So we will subtract this. This is the actual volume of gas. Now for N moles, what it will come out to be? V minus NB. Now what will be the correction? It will be P. See, the formula was PV is equals to nRT. Now it comes out to be PV into V minus NB is equals to nRT. Why NB? Because we are talking about N moles. Now this was pressure correction. Now we will see, this we have already done. I am writing pressure correction over here. V minus NB is equals to nRT. Now we will see our next case, that is the pressure correction. Now if I talk about the pressure correction, let us see. As the molecules are big in size, they are rigid. So what will happen over here? If this is our container, this is my, let us say, molecule A, and these are my other molecules. Now as you know, in ideal gas we said that the molecules are such small that there is no interaction between them. But in real gas, when the molecules are big, they will have interaction between them. If this molecule is being collided at this wall, now what these molecules will do? They will also attract, they will also interact with these. Force of attraction will occur. And ideal gas was hypothetical state which told us that there is no interaction, but interaction is occurring. And due to this interaction, students, the pressure came out to be different. They are applying the pressure on this molecule. This molecule is being hit with the wall and colliding and bringing a pressure. So the pressure of the gas now, Pressure of the gas is increased. Pressure gas came out to be the pressure which was present earlier plus pressure which is present internally. Now we will find out the internal pressure first. To calculate internal pressure, what is the concentration of the molecules which are present near the wall? Let us say these are A molecules, these are B molecules. So the concentration of A molecules comes out to be number of moles by volume V, because concentration is number of moles by volume in solution. Now let us say the concentration of these B1, it also comes out to be number of moles by volume. Now if I talk about the pressure internal that is occurring will depend upon whom? On A molecules and on B molecules. So it is directly dependent upon A molecules and B molecules. That means it is directly dependent upon the concentration of A molecules and concentration of B molecules. N by V into N by V. So what comes out over here? N square by V square. Now to get rid of this directly proportional side, we will use here A. To get rid of this, we will introduce a factor A over here, right? Now in this formula we can write the pressure of gas. Now see, we have calculated pressure internal to be A N square by V square, right? Now pressure of the gas will be equivalent to what? Pressure plus A N square by V square. So this is the pressure correction term. Now applying this on the previous equation, what we are getting now? This was the previous equation. Now applying pressure correction as well as volume correction, what we are getting? P plus A N square by V square into V minus NB is equals to nRT. Now this is the equation for your real gas. Most very important one, in which you are going to see a lot of numericals. Is it clear to you, students? Now comes our last segment, that is inversion temperature. Basically inversion temperature, it is a theoretical concept you need to understand. If a compressed gas, the compressed gas is allowed to pass through a fine hole, students, it may show cooling or heating or no change in temperature depending upon the temperature of gas. All of these depend upon the temperature of gas. Are you getting my point? For each gas, there is a characteristic temperature which is known as inversion temperature. Every gas exhibits that. Now, if temperature is, Ti, that means inversion temperature is less than the temperature which is normal, then heating is produced, and if it is more, then cooling is produced. When they are equivalent, then neither heating takes place nor cooling takes place. And this is your formula for the inversion temperature. Okay, now students, this ends our chapter, but before ending we shall practice some of the questions over here. I have taken a lot of questions in the DPP for you. Why? Because in this one-shot video lecture, I want you all to understand all the concepts in detail so that you can apply on the DPP sections. And I want you to attempt the DPP, attempt the questions, try again and again, because in the DPP, I have taken previous year questions for you. That will help you to know how the question rises. All will be based on the formulas which I have put a star mark. All of them are based on that formulas. Okay. Now let us see some of the theoretical questions also, because that questions you can practice also and these also. So let us see. The types of attractive forces between a polar molecule and non-polar molecule are: A option is dipole forces. B option is hydrogen bond. C option is induced dipole forces. And D is dispersion forces. Okay. Now, if you remember, students, I told you dipole were the one in which both were polar. Both had the poles. For example, HCl. But it is asking about a polar molecule and a non-polar one. So it can't be option A. Now if I talk about second, B option, hydrogen bond. Hydrogen bond arised in fluorine, oxygen and nitrogen when the electronegativity difference was there, when one's molecule more electronegative atom was attracted towards the next molecule less electronegative atom. So this also can't be there. C option says dipole induced dipole. When I am feeling a little bit depressed, my parent comes and motivates me. So that is dipole inducing another dipole to develop a charges. So see again here, when a polar molecule induces a non-polar molecule, the type of attraction comes out to be dipole induced dipole forces. So the answer which is correct is option number C, students. Is it clear? Okay. Now let us see the next case. We have, which of the following graphs represent the correct Boyle's law? In which of the following is the Boyle's law represented correctly? Now what was Boyle's law? Boyle's law stated that temperature is kept constant. If you remember, temperature was constant, and when one of the state variable is kept constant, we will establish the relationship between other two, that was pressure and volume. Pressure and volume. And when we saw the relationship between both of these, pressure was inversely proportional to volume. So when we are going to develop a graph between pressure and volume, it came out to be straight line, because here it is represented like this. So it came out to be straight line. So first is correct. Okay. If I talk about the second situation, when you are obtaining a graph between PV and P, this comes out to be this line, and it is also correct. Okay. Now this was new to you to understand. You can also mention in your previous notes. Now let us see the third case. When I talk about pressure and volume, see, if I am drawing a graph between pressure and volume, I know that more the value of volume, less will be the pressure. Less will be the volume, more will be the pressure. So a hyperbola graph was obtained. This is also correct. Now if I talk about fourth case, no, this is wrong. Whenever I am talking about pressure and 1 by V, I obtain a straight line. So which option will be correct? First, second and third. Hence option number A is going to be the correct answer. Is it clear? Good. Now students, comes our next question. A graph is plotted between pressure and volume at different temperatures. Here you can see at 100 Kelvin and at 150 Kelvin. On the basis of the graph, what changes will you observe in the volume? What are the changes that you are going to observe if the pressure is increased at constant temperature? Second one, the temperature is decreased at constant pressure. So see, when pressure is increased at constant temperature, we know that pressure is inversely proportional to volume. When pressure will be increased, volume will be decreased. So first situation, volume decreases. Okay, now for second, the temperature is decreased at constant pressure. Remember, at constant pressure, we established a relationship between volume and temperature. Volume was directly proportional to temperature. Temperature being decreased will decrease volume also. So in both of the cases, volume decreases. So let us read the options. A option says volume increases in both the case. No. B option says volume decreases in both of the case. Right. So answer number B will be our correct answer. Okay. Now let us see the next question. Absolute zero can be defined as the temperature at which? A option, pressure becomes 0, B option, volume becomes 0, C option, mass becomes 0, and D option, density becomes 0. So here students, volume will become 0, right? So this is what absolute zero can be defined as. Now comes the next question. Gaseous mixture contains 56 grams of N2, 44 grams of CO2 and 16 grams of CH4. The total pressure of mixture is 720 mm of Hg. It comes out to be 720. Let me check the mic once. I guess there is issue. Okay. Okay. The pressure comes out to be 720 mm of Hg. The partial pressure of methane is, A option is 75 atm, B option is 160 atm, C option is 180 atm, and D option comes out to be 215 atm. Now students, what we need to do is, we know that the partial pressure of any substance is equals to the mole fraction of the substance into the total pressure. So total pressure is given to you, that is 720. You need to multiply it with the mole fraction. We need to calculate mole fraction first of all. To calculate mole fraction of a particular substance, what we need to do? To calculate mole fraction of methane, we need to calculate the number of moles of methane divided by total number of moles. Now for total number of moles, we need to calculate all the moles. Okay, let us calculate moles for N2. Moles comes out to be given mass upon molecular mass. Given mass here is 56. Now what is molecular mass of N2? Nitrogen has 14 and there are 2 nitrogens, so it will be 28. It will be 28. So it will be 2. It comes out to be 2, right? If I divide this. Now students, if I find out number of moles of CO2, again given mass upon molecular mass, what is the given mass of CO2? It is 44, and the molecular given mass is given 44, and the molecular mass also comes out to be 44. So number of moles comes out to be 1. If I talk about methane CH4, given mass is given to us 16, while molecular mass of methane is also 16. So number of moles comes out to be 1. Now what is the total number of moles? It will be 2 plus 1 plus 1, right? So here mole fraction of methane will come out to be, number of moles of methane is 1 and total sum is 4. So mole fraction comes out to be 1 by 4. So partial pressure is equals to mole fraction into total pressure. Right, my dear students? Now we are going to divide this. It is 180 atm, students. It comes out to be 180 atm, right? So the option C is going to be your correct answer. Is it clear to you? Great. Now, thank you so much, students. This video lecture ends over here. This chapter ends over here. I want you all to practice DPP because I have taken a lot of questions there. A lot of questions are being assembled to you. All the previous year questions are being given to you so that you can apply all your concepts over there, all your formulas over there. And yes, you need to practice this concept again and again to make it stronger, right? So whenever you are studying, kindly listen to the video, and after that practice all the questions because practice will make you perfect, right? And I will end with the same quote that I started with. Okay, so where there is a will, there is a way. So never forget that. Keep this in your mind. Whenever you are depressed or sad, you feel like I'm unable to do questions, just think that you need to reach your goal, you need to achieve your goal. So the way will automatically come out when you are going to try. So try and try again and again, again and again, and you will achieve your success. So we will meet in the next video lecture with the next topic. Till then, keep smiling, keep learning. Thank you so much.